You hear it everywhere, right? The future is electric. We see all these sleek new cars, we hear these promises about a clean energy revolution, and, well, it all feels pretty inevitable. But what if I told you that a fundamental law of physics, something as basic as how much energy you can pack into a certain weight, presents a colossal challenge to that vision? Okay, let's really get into this. Look, the excitement is totally real, and the technology is getting more impressive every day. But behind all the headlines and the hype, there's a physical reality we just have to grapple with. It's the one thing that explains why your car might be electric one day, but the plane you fly in almost certainly won't be. Not for a long, long time, anyway. And the vision is so compelling, isn't it? I mean, a world powered by batteries, with these silent cars just gliding through our cities, zero tailpipe emissions, a grid running on sunshine and wind. It's a really powerful and attractive future, and it's driving a ton of investment and innovation. But to really understand the true scope of this transition, we can't just talk about the vision. We have to talk about the physics. And it all boils down to one single, incredibly important concept: energy density. This one idea, seriously, is the key to understanding the entire energy landscape. So, what is it? Well, to put it simply, energy density is just how much punch you can pack into a certain amount of stuff. You can measure it by volume, like a gallon of gas, or you can measure it by weight. And for anything that has to fight gravity, like a car or especially a plane, we care most about gravimetric energy density. In other words, how much energy can you store in every single kilogram of a fuel source? And this is where the story gets really, really interesting. Because when you put our traditional fuels head to head with our best batteries on this one single measurement, the results are, well, they're staggering. Let's just look at the numbers. First up, let's consider the undisputed champion of energy density. It's the liquid fuel that has basically powered our entire civilization for a century. We're talking about kerosene, jet fuel, gasoline. They're all pretty much the same in this respect. A single kilogram of jet fuel packs an incredible 12,200 watt-hours of energy. For my American friends, that's over 5,500 watt-hours per pound. That is a massive amount of power and a very, very small amount of weight, which is exactly why it's been the foundation of global mobility for so long. Okay, now let's turn to the challenger, the lithium-ion battery. This is the technology that powers everything from your phone to the most advanced electric vehicles out on the road today. So the best commercially available EV batteries, they come in at around 300 watt-hours per kilogram. That's about 136 watt-hours per pound. And yeah, you heard that right. Not 12,000, but 300. The difference is just enormous. And when you see it on a chart like this, the difference becomes completely undeniable. This isn't a close race. It's not even in the same league. To get the same amount of energy, a battery has to be about 40 times heavier than gasoline. 40 times. This scientist and energy expert, Vaclav Smil, really puts it bluntly. This 40-to-1 gap isn't some minor engineering hurdle we can just solve next year. It's a fundamental physical constraint that shapes the entire energy transition. You just can't innovate your way around a number that stark. So this brings up a really critical question, right? If you have to carry around 40 times more weight in batteries just to get the same energy as a tank of gas, how do electric cars even work? I mean, how can they possibly have a decent range? Well, this is where the electric vehicle has a secret weapon. Because it turns out, it's not just about how much energy you can store, it's about how efficiently you can use it. And this is where the electric motor completely changes the game. The huge difference here really comes down to waste. An internal combustion engine is basically a series of controlled explosions, and it's incredibly wasteful. About 3/4, 75% of the energy in that gasoline is just lost as heat before it even gets to the wheels. But an electric motor, it's stunningly efficient. About 90% of the energy from the battery goes directly into making the car move. So here's the crucial point. That incredible efficiency claws back a huge portion of the energy density disadvantage. So while the battery might be 40 times heavier for the same energy, the motor is about 4 times more efficient at using it. For a car, this trade-off actually works. It effectively narrows that massive 40-to-1 energy gap down to a much more manageable 10-to-1 weight problem. But, and this is a really big but, this energy versus efficiency trade-off is not a universal solution. What works so brilliantly for a 1-ton car completely falls apart when you start dealing with much, much heavier vehicles. And this chart just lays the problem out perfectly. For a car, the need for energy density is okay, it's manageable, and the EV's efficiency advantage is high enough to make it work. But for a jumbo jet or a massive cargo ship, energy density is absolutely critical, and the efficiency gains are nowhere near enough to overcome that 40-to-1 weight penalty. Think about this for a second. On a long-haul flight, almost half the takeoff weight of a jumbo jet is just its fuel. If you tried to replace that kerosene with today's batteries, the batteries alone would weigh many times more than the entire plane is even allowed to. It would simply be too heavy to get off the ground. So, when we zoom out, this concept of energy density gives us a much more sober and realistic picture of the whole energy transition. It's not just a matter of willpower or policy, it's a battle against the fundamental physics of mass and energy. So, what you should really take away from all this is that the problem is way more complex than it might seem on the surface. Yes, electrification works for cars, and that's because of the incredible efficiency of electric motors. But that 40-to-1 energy density advantage that fossil fuels have, that remains the central, unconquered challenge for decarbonizing things like aviation, shipping, and heavy industry. And that leaves us with a final, crucial question. The laws of physics, they're non-negotiable. They don't bend to our wishes or our timelines. The challenge, then, isn't to somehow break these laws, but to be clever, to be realistic, and to be truly innovative within them. And that, my friends, is a much harder but a far more important task.